Hi, this is Ana Douglas with the third video of the module Wave Optics for the course ECE 513 Intro to Optics and Photonics. In this video, we're going to identify the relationship between ray and wave optics. We're going to introduce a procedure to estimate the wave function using the Eikonal equation. We're going to understand the meaning of the optical interference as the summation of the complex amplitude distributions and not the optical intensity. We're going to derive the total intensity distribution of two waves based on their phase difference. And we're going to distinguish constructive and destructive interference and deduce the condition of constructive and destructive interferences for two plane wave where one of them is slightly delayed along the z-axis. So as we were saying in the other videos, we can write any wave is going to be represented by a complex amplitude. So we're going to have its amplitude distribution and then we're going to have its phase distribution, right? And if it's an optical waveform, means that the Helmholtz equation needs to be satisfied. So the Laplacian of the complex amplitude plus the wave number squared multiplied by the complex needs to be equal to 0. If we write the complex amplitude in terms of their phase and amplitude, then we're going to have an equation for the real that is going to be divided between the real part and the imaginary part, where both the real and the imaginary part are going to depend on our phase and the amplitude, and both of them needs to be equal to 0 if we are satisfying the Helmholtz equation. So the real part is the one that is going to be related with the optics, ray optics. And this is the one that is giving us the module of square of the divergence of the phase. And this is going to be related with the Laplacian of the amplitude divided the amplitude. So this is going to be our Eikonal equation. And basically the Eikonal equation, what it's telling us is that the light travels the path with minimum optical path length, which in the case of a uniform refractive index, that's gonna be a straight line. And that's something that we already introduced as a principle in module number 1 in ray optics. So if there is a particular case that is simple, which is for paraxial approximation, where in the paraxial approximation, we are assuming that the amplitude change really slowly compared with the wavelength. So this term is going away, it's really small than 1. So at the end, the divergence of the phase, it can be approximated as our refractive index. So we were saying that we're gonna introduce some procedure to estimate the complex amplitude. So the procedure is, the assumption is that we need to know the refractive index, how the refractive change across the space, the spatial coordinates. So we're gonna use, knowing that we know the refractive index, right? We can use the Eikonal equation to express the divergence of the phase, to have the relationship between the phase distribution and our amplitude. Knowing that we know that function, then we can go to the imaginary or to the real part of the Helmholtz equation, and then putting that relationship, we're gonna have a single equation that it's only gonna depend on the amplitude distribution. So we can solve this equation to estimate the amplitude distribution, and when we know the amplitude distribution, we go back to step 1 where we wrote the phase as a function of the amplitude and we solve for the phase. That's the procedure to estimate the complex amplitude distribution using the Eikonal equation. So when back on the day they were studying optics, they understood the dual modality of the rays as a wave, because the only way to explain the superposition of two optical waves was if the light was acting as a wave versus as a ray. So what that means is that if we have two or more optical waves that they have the same temporal and spatial frequency and they meet in the same region of space and time, then we're gonna assume that they're gonna superpose, so that we're gonna have a summation of their individual waveform to generate a total wave function. So this superposition occurs on the wave function, but does not mean that it's the superposition of the optical intensities. And we're gonna work and we're gonna show how different that could be in a couple of slides. So this is at the end where it's telling us is that the superposition, the interference, we're gonna see as changing of the optical intensity between maximum and minimums. And basically it's gonna depend on the phase difference between the two waves that we are superposing. The way of measuring optical interference is using an interferometer. There are different types of interferometer, but basically we have the Michelson or the Fizeau interferometer, where you have a beam splitter that divide the original source in two. So usually one is the object and the reference. In the Michelson, you have two mirrors that reflect back, but you can replace one of the mirrors by a reflective source. And definitely you can make a little more complicated putting some optics within the middle. The math center is basically that you have the beam splitter, and then each of the waves get reflected by a mirror, and you use another beam splitter to combine them. And the Shanghai interferometer, that's kind of like you have three mirrors, one beam splitter, and basically the object and the reference wave, they travel the same path length, just in opposite directions. So one goes up and then you make the circle, which is kind of like the red arrow. And then the reference, for example, the other wave, you cannot do the backward path wave. And then you just meet again your beam splitter and leave it. So what is super useful for optical interferometers? So one of the applications that I'm really into, it's about digital holographic microscopy. So basically the idea is that some of the sample, especially like low dispersion sample, like cells, biological cells and thin tissues, they are mostly transparent when you illuminate with white light, so you don't have enough contrast to image them. But they change the wave distribution of the light. So we were saying that the interferometer or the interference occurs because there is a phase delay between the two waves, right? So this samples is going to introduce a phase delay between the two arms that we can measure having a interferometer. So here there are two different of interferometers that I have in my lab. One is the typical math center, where the only difference is that we introduce in one of the arms a microscope objective lens, like a microscopic system. So we enlarge the area that we want to image. And the other one is a modified math center. So it's kind of like math center with a little, like here on the middle is like a Michelson, where your sample is reflective, and you're just gonna use them more for material science. But the idea is like when you record your interference pattern, you can process that interferogram to get your information of different type of samples. So this technique that is called digital holographic microscopy so provides you information about the phase, and it's quantitative information, and it's really useful for life science and material science. So in life science, definitely it's low cost, you only need one single image, so it allows you to do live cell imaging. It's quantitative, so you can provide some analysis when you are comparing different cells, especially if you are doing like disease diagnosing screenings or some drug discovery. For the material science, like we are more interested to see the topography and see if there is some defect or how we are characterizing the surface and doing some analysis. So those are like some cool videos that you can see from the technique. All right, so let's assume that we were saying that the two wave needs to have the same spatial and temporal frequency. So we needs to simplify, that means that if we have the same temporal spatial frequency, that means that it's monochromatic, so they are characterized for a single wavelength. And we have here our first wave with the amplitude and the phase, and then the intensity, where if you see the intensity is just gonna be a1 square, so we lose any phase information. We have exactly the same for the second one, where again the intensity is only gonna be the square of its amplitude, and the resultant, because they are coherent superposition of the wave functions, it's gonna be the summation of every wave function. So we were saying that the superposition occurs by summing the individual complex amplitude distribution of the wave function. So then the intensity distribution of the superposition is just the modulus square of the resultant complex distribution, which is going to be the summation of the individual one. And then if we can do the intermediate step, so we're going to have the modulus square of the first one plus the modulus square of the second one plus the first with the second complex conjugate, and then the first complex conjugate with the second one. And every time that we have the modulus square, that's the amplitude. So the intensity is just r squares of the amplitude, and then r having expressed its complex distribution as the phase composition, then at the end what we're gonna have here is just the amplitude, the double of the multiplication of the amplitude multiplied with the cosine of the phase. So as you see, the intensity pattern is proportional. It's gonna change with the phase difference between both interference wave. And we need to be extremely careful because it's linear. The complex amplitude of the resultant is linear with respect to the complex amplitude, but not the intensity. The intensity is not the direct summation of the individual intensity of the interference wave. So this means that our intensity pattern is gonna change based on the phase difference between both waves, right? So what we have here is that, as you can see from the profile, right, is how the intensity changes. So the total intensity is gonna change from a maximum value and a minimum. And we can see that the interference makes a spatial distribution of the optical intensity. So there are spaces where we have maximum or minimum intensity without a violation of the power conservation. So again, I was saying that we're gonna have kind of like a minimum and a maximum optical intensity. So the maximum is what we're gonna call the constructive interference, and is when our cosine of the phase difference is gonna be equal to 1. So remember that this is the phase difference. So phi is the phase difference between the two interference wave, and then the minimum intensity is achieved when the value of the cosine of the phase difference is equal to -1. And the total intensity, we're gonna keep changing between the maximum and the minimum. The minimum value is gonna be equal to 0. So we're gonna have a total intensity cancellation of the two interference waves when both waves have the same intensity. Otherwise, the destructive interference, like a total blackout in the destructive interference, is not gonna to achieve. But think about it, like it's gonna be a space, and I want to repeat that one. It's gonna be points in the space where the intensity of the interference is gonna be maximum, and they're gonna be points in the space when the total intensity is gonna be minimum. To finalize this video, let's do an in-class problem. So they are saying that we have two plane waves that assign the same intensity propagating around the z-axis, and one of the wave is delayed by a distance d, and we need to find the condition of constructive and destructive interference based on r d, the delay distance, and the wavelength. So remember, we have plane waves. So the first wave, this is gonna be some intensity, and then the linear complex exponential. So this is gonna be our plane wave traveling along the positive, traveling along the plus c direction. And then we have the other wave, which they told us that they have the same intensity, so I'm just gonna put here the same intensity, but now they say that they are delayed, so that means that we're gonna have c minus some distance d, because this is gonna be our delay that the problem statement is telling us. So when we do our intensity of the superposition, we know that the superposition is linear to the complex amplitude, and definitely we already know how to proceed. We're gonna have the absolute modulus square of the individual complex, and then each of the multiplication where one of them is conjugated and the other one is not, so the cross terms. So the first one is just gonna be our intensities, which are gonna be the same, and then the other terms are the square root of the intensity, and they say here minus jkc, and then we have jk, we need to complex, and then c minus d, and now we're gonna have the other term, which I'm missing here, a square root of the intensity. So it's gonna be the square root of the intensity, the other square root, jkc minus jkc minus d. And when we simplify it, we can see that, for example, this term, we have minus jkd, and then we have that's not d, that's a c, jkc, jk, and then we have here c, and then here we have minus jkd. So the term along the c, they cancel each other, so we have a term with kd, and here we're gonna have the same. By now we're just gonna have the positive one. This term is gonna be the intensity, so at the end our optical intensity of the interference is gonna be, I can take outside my total intensity of the individual, and then we're gonna have 2 plus 2 times cosine of k d, which is gonna be our delay. So our intensity, our total intensity, changes with the delay between both both interference waves, and it's gonna be the individual 2 plus 2 cosine. But instead of writing with the wave number, allow me to write it in terms of the wavelength, so 2 pi over lambda. And then here we have our delay. So we're gonna define, we say that we're gonna have constructive and destructive interference, but the constructive interference is the one where the total intensity is maximum. So that means that the cosine is gonna be equal to 1, and that means that the argument of the cosine, so 2 pi over lambda d, that needs to be a multiple of 2 pi m, where m is just any integer value. That means that if you see here, the 2 pi cancel with the other 2 pi, so our d values needs to be a multiple of lambda. So this means so the delay between the two needs to be multiples of lambda, and for that particular case, our maximum intensity is gonna be 4 times the individual intensity of an individual wave. Versus to the constructive, we're gonna have the destructive interference, which is gonna be the value of the intensity where it's gonna be minimum, but because we are assuming that both of them have the same intensity, that's gonna be equal to 0, and that's gonna happen when the cosine is gonna be equal to -1. So that means that the cosine, the argument of the cosine, so 2 pi over lambda d, that needs to be equal to a odd integer of pi. So remember, m is gonna be any integer, and then this is gonna be a odd multiple of pi. So if we write this condition in terms of where is gonna be the delay between our interference, then here we know that the delay is gonna be a odd multiple of half wavelength. So this needs to be an odd multiple of the half wavelength. And these are the conditions to have destructive interference when we have two plane wave and one is slightly tilted. I hope that you get a better understanding of the interference and wave to measure. Thank you.